All right, hi everyone. It's better if we talk and say something, right? So that we can feel safe there listening to us. So this is a very important moment for two of our graduate students, because we will have back-to-back, like in football, presentations here. So I will start introducing you to Kahlin Wacker. We will be a little more formal than usual, because Mr. Walker here is a soil scientist from Utah State University that joined Mark's lab in the fall of 2021. So since early April, I have had the privilege to work with Kahlin, and we got to an important moment where he's going to enlighten us with his research activities. So without further ado, I would like to let our star of the afternoon to start his exit seminar. The way it will work, he will give us a talk, and then we will have time for questions. So we will start opening that up for Tifton and Jerkin people, and then we'll open for you, and then Peyton Pasha will start over at 4. Right? Elaine?
All right. Welcome everybody, and welcome everybody on Zoom who hopefully is not asleep yet. But we'll get to that when we get there. So what I worked on was working on automated image collection analysis for CEA, for controlled environment stuff, but trying to make it so it can be for anybody else who wants to do it. And I've had the privilege of working with Mark and with Renito over the course of this process. It's been kind of 2 for the price of 1, because I've gotten to get the perspectives of 2 different professors over the course of their master's degree, which had its growing pains, but it's been in the end positive. So that's not a good sign. All right, so introduction. I got out here doing imaging, and there was a couple of reasons why we got into imaging, or why Mark got into imaging, and then I got roped in by Mark further down the road. So it's fast, it's easy. How many of you guys have ever had to take one of those like chlorophyll meters, or the little things that you clamp on the leaves, little ones you have to clamp on the leaves and then put the little shutter over and leave it for 5 minutes? And then, yeah, we've all felt the pain. And then you've got to make sure you're truly being random, don't have sample. Anyway, it's a mess. With the imaging, it does the whole dang canopy. And then it just takes an average of the whole canopy. You don't have to worry about your sample bias, whether or not you spend enough time where you're squeezing it on there hard enough. So with this, so on top of that, it's non-invasive, because for some of those, you mess up some of the photosynthetic action of the plant. And if you squeeze some of them too hard, you start causing damage. But this is non-invasive and it's non-destructive. And so we can get a projection or an estimation of the canopy size, or more accurately, the 2-dimensional area of the canopy size, without having to tear off every leaf and shove it through a little conveyor belt, which some of you guys have also done, and I'm sure you all enjoyed that as well. But with the imaging, we're looking for that canopy size, but then we're also looking for those pigment concentrations, which are often indicative or are stress symptoms. So the beautiful thing about the system that we've got, compared with a lot of remote sensing type imaging, is that we've got spatial information to play with. So we can make decisions, so we can use that to determine areas of different priorities on the plant. So what we started with this sucker. This is the top view imaging system made by Harris in the Netherlands. So Mark wanted to get into imaging, so he bought this thing. The other thing he was using was a standalone chlorophyll fluorescence imager, but we'll get to that again in a second. So this is multispectral. It's got 8 channels, really fancy. It's in a nice cart. One of the things that I'm deeply envious of are the little wheels and the rigidity of the whole affair, which is really nice. But what this does is it generates monochrome images under 8 different colors of LEDs. So, and then it gives you a black, so monochrome being black and white, it gives you each of those images, and then you can use those for whatever you like, and we'll get into that in a minute as well. But that sucker is expensive. And on top of that, it doesn't do any of the analysis itself. It gives you all the images back, and then you got to figure out what to do with them, and you've got to do that, which I don't know if any of you have tried to process images one by one in ImageJ or a similar program. that's also painful, would not recommend. You can make a macro and that helps, but it's still not as, it's not as fast as painless as one might like. So, which brings us to our imaging system. So the why and the how. The why is that last bullet point. That image, that top view system and others like it are expensive. And they don't, and at least in this particular instance, it doesn't do the analysis for us. And so we're stuck with a bunch of very nice images and no application data, and nothing we can truly turn around and apply without doing further secondary processing. And so we then built our own. So the original prototype was built the summer before I arrived, I believe, by a summer high school intern named Benjamin Sidor, who was there to kind of learn some of the ropes and just work with Mark. So, and that was very effective. I got in there, and if you look, this first picture here is, so you can see that little camera module right here and that big dark spot. So this is the first version that Benjamin worked on with help from TC and Chung-Hyun and Mark directly. And so it just had this little, so it had the camera peeking through a hole in this diffusion plastic. And then it has, and then this is where the Raspberry Pi microcomputer and all of the wiring was situated. So what I did when I got this was the big piece that I added from a scientific perspective was this chunk right here in the middle. This is a chlorophyll fluorescence imaging peach, that module, sorry. So what this does is this has the camera mounted to it on the backside, but the way that chlorophyll fluorescence works is you hit a plant with blue light and it lights up in the red and far red spectrum. So that little blue, so that filter that's on there, that filters out everything down into the, down below the reds. And so you light up the blue lights, you take a picture, and the only thing you can see is anything that's photosynthetically active, which causes a bit of a problem when you've got algae in your pots. But other than that, the rest of the time it works great, because that allows you to segment the images, because a lot of the pain that people feel is separating plant from background. Because in a lot of remote sensing applications, and at the company that I worked at before my undergrad, we dabbled in NDVI, for example. But that was a field-based thing where it was a single giant pixel, effectively. And so NDVI in those particular field applications was kind of an average of the dirt in the plant. So it was more or less presence of plant rather than the true measurement of plant health and the uniformity thereof. So, but this allows us to segment the plant from the background so we can actually look at what the plant's doing and not averaging background in with dirt, in with plant, in with grow tent or whatever else. So this is what we ended up with. So when we started out for this, we were shooting for a hardware cost of about $500, and then supply chain stuff kind of bumped that up to about 600. So this is the itemized list of effectively what we spent to build our imaging system. If you'll notice, the LED cost is kind of high. That's because for our first version, we got nicer LEDs with guaranteed spectra. So we made sure that we got it right the first time. But the further we've gotten along, it turns out you can use cheap generic LEDs and it's fine, as long as you're careful about which cheap generic LEDs you pick. And then that drops the cost back down to about that $500 value we were shooting for. So the real benefit here, so yeah, you can get an imaging for $500 or $600, but the real value is the learning opportunities. Well, okay, part of the value is learning opportunities, because so this force fed a whole bunch of us a whole lot of applications grade Python, and then having to do wiring. So with this, there were some wiring lessons learned. We were a little bit too liberal with our use of quick connects, and we ended up having intermittent connection issues for a while. So we had to go through and resolder the whole thing. So I've rewired this entire thing twice, but it works now. So you learn how to code, you learn how to wire all of these parts. So this part right here, that little arm that holds the filter, that camera module, those are all 3D printed parts. And so Mark, Benjamin, Chung-Hyun, and I all had to do some amount of CAD work to be able to make these parts, and then subjugate the somewhat recalcitrant 3D printer to our will to get useful parts out of it. But what that gives us in the end is a Raspberry Pi that will analyze all of the images we take in real time, so we can just pull one giant CSV with all of the numbers in it that we want to play with, and we don't have to sit there and fight with a whole pile of secondary code to get the images analyzed, which was a nightmare for my first trial. So this is going to be a video that better be muted because I've been fighting with that all week. So this kind of demonstrates how directly that imaging system works. So where it turns on a given light, takes a picture, turns it off, turns on the next light, takes a picture. So we've got effectively, so this is a picture of the red parts of the plant, the infrared, the blue and the green, and we can stitch the red, blue and green together to make a color image. And this over here is where the magic happens. That's the chlorophyll fluorescence image. Segmentation, if you ask anybody who does imaging, is kind of a nightmare. So Jonathan has been working also on imaging more in like in a greenhouse situation. So for this particular system to work, you've got to be in a controlled sole source lighting environment. For what Jonathan is doing, he is integrating a thermal camera. He's got a Kinect camera to get three-dimensional images out. You've got a near infrared camera, multispectral, and then a color camera attached to a Raspberry Pi as well. So he's got the whole gamut of things, and so he's going to have some fun stuff when you get a seminar from him. But it's still the segmentation that's hard. He's using a machine learning approach, which has benefits that I did not have. So I'm a little bit jealous of that, but it's working. And with this, that allows us to cut the background out so we don't have to keep the imaging system clean. And so we can just kind of shuck plants in and out of there. So this is what the image analysis process kind of looks like. So this is a little chunk of the code. So you can see there on the scroll bar on the right about how much of the code you're looking at. And this subroutine right here is the thresholding. So this takes that chlorophyll fluorescence image, it thresholds it, so it figures out where. So because it generates a histogram, finds the point that's between the background and the foreground, and then it cuts those two apart and makes a mask image that we can use so it only looks at the plant parts. So if you want to talk more about Python and pain later, come find me. I would love to share. So then the index that we used, so we talked about taking all these images. So the index we use is kind of a tool to leverage those images into being more useful. So NDVI is normalized difference vegetation index. And what that ends up giving, so you can see we've got the color images right here, and anybody can tell you that that plant's not real healthy, but there's no good way to quantify that in a repeatable way because everybody's eye is a little bit different. If you're having a bad day, maybe you're angry at the plants, as sometimes we all are, you may judge them a little more harshly. But if you change that to NDVI, for example, and then you graph that, you have a hard number for what exactly is plant and is not happy. So you can see in this histogram, we've got two peaks here. So this peak is background, and then this peak is that unhealthy leaf at a darker value, and the darker value is here. And then this peak is the healthier leaves over here. But that gives you an average NDVI of 0.27. And because this is just the plant, if you have one unhealthy leaf, it drags your average down and it blows up your standard deviation. And so here we've got a healthy plant, and so that's a very, very tight peak and a much higher average. And so that kind of gives you a quick and dirty way to say, hey, is there chlorosis somewhere on the plant, or is there a leaf that's dying or something like that? Because that average just kind of gives you a snapshot of what's happening. It's effectively a measurement of greenness, for lack of a tactful way to put it. But the other beautiful thing is it gives us that spatially resolved information, so we can know if we really want to, we can figure out how much of the plant is at what levels of NDVI, or what variety of reflectance it is. And we've got those areas to play with, which is kind of fun. So my other chapter, the first chapter is putting that imaging system together and disseminating it to the world so other people can go forth and do whatever they want with it, because it's easy to add other indices or whatever analysis you want. So the supporting data. So I ran two different trials. The first trial was kind of a validation of the imaging analysis code to make sure that was completely functional. We used the top view system to take those images, and then we analyzed it ourselves. Then the second trial was imaging and analyzing with all of our own hardware and software to make sure that everything was still working. So the goals of these were to induce changes or differences between the treatments and stress in the plants. So all grown out in the greenhouse in these fun little flood trays, so they were sub-irrigated. And the first trial grew all the plants in peat and then applied different rates of Carroll's controlled release fertilizer to them between 0 and 8 grams per pot. And then the other trial that I ran was with different pH levels, and because it was such a nightmare getting the substrate to be a consistent pH level, we ended up just doing kind of a stabilized hydroponics method in rock wool and then irrigating with the desired pH fertigation solution. So for both these trials, I had 8 plants per treatment per cultivar. Here we've got kind of proof of concept a little bit, where we've got our fertilizer rates on our x-axis there. And then we've got our dry weights and our projected canopy size. So that projected canopy size comes from the imaging system. It takes a 2D picture. It's like how much of that is plant. And then you have to calibrate between from pixels to area. And so in this particular instance, it's in pixels. On the next graph, you'll see a square centimeter area. And so the fertilizer and the dry weight. So this particular trial worked pretty well. We got pretty consistent plant biomass differences. And in the end, what we're shooting for is optimal biomass production in something like this. So we can see that we can see the differences there where at the different rates of the treatments. And so this is the growth rates. So this is the plant size on the days that we image. And then we've got the plant area there in squared centimeters. So, and the fertilizer treatments all stack out really nicely, but as they've got the different rates of growth. And so we could pick that out just purely from the area imaging, which kind of fun, but not in the end what exactly we were looking for. And so then what we were trying to get to work was correlating NDVI, or the average NDVI in the plants, against the fertilizer rates that we applied. And that worked fairly well, if I do say so myself, but I'm a little bit biased in favor of the data at this point, and pretty happy with how that shook out. So each of these points is an average of 8 plants, and then that's the standard error in each of the little whiskers on the points. So then the pH trial. Why did we do that? In hindsight, we should have run another fertilizer trial, but that's the benefit of hindsight. So what we were shooting for was inducing micronutrient deficiencies, and then hopefully by doing that, getting visible changes in the canopy. So these are two example nutrients these are two example nutrient contents and concentration, well, concentration and content if you go from left to right, of the Super Cascade Red cultivar. And so that worked. The NDVI paired with the pH did not work quite as well. So the only one of these that has anything approaching a statistically significant factor here is the Super Cascade Red. At the suggestion of my statistician, she suggested that the p-value in this particular instance, where it is over 0.05, is in fact significant because there were a couple of pretty considerable outliers in this data set. And she figured that this could be safely interpreted as significant, knowing what we know about those outliers and seeing where the rest of the data points fall. So, because this is just a graphed average, because those graphs get pretty busy when you've got 96 more points on there between the three graphs. So, and in this instance, this is where it becomes valuable to have other indices. So, one too many, there we are. So now we jump over to the chlorophyll fluorescence images, or chlorophyll fluorescence index, sorry. So these are graphed against that percent phosphorus and the parts per million of manganese that we saw in that first pH section graph. So, and this also demonstrates really well why you've got to have multiple cultivars in a given trial, because you'll have cultivar specific dependencies that happen depending on what you're doing. So in this particular instance, the carpet blue and the wave purple are not particularly great in either case, but the Super Cascade Red checks out really well with the chlorophyll fluorescence and those nutrient rates. So, and then if we graph those against pH, things get a little better. So where it's kind of the combined effects of all of the micronutrient deficiencies that start to bring wave purple into near compliance in a way with being statistically significant. Whereas when we add everything, suddenly the Super Cascade Red shapes up fairly well, and the carpet blue is still kind of a mess, which is it's a little bit interesting to see how there are the different dependencies in the different cultivars, because in the first trial with the fertilizer, Super Cascade Red was the one that was a giant mess. So it's interesting to compare how you get those differences between the two cultivars, well, the three cultivars in this case, and that's why it's important to try different cultivars. So in conclusion of all of this, the objectives that we had were to make an imaging system that It was simple enough that anybody could build it, complex enough that they could build it and they learn from it so then they could have further research tools. Because I imagine if you talk to anybody else in the lab, the things that they've learned from having to work on and build these different things have helped them improve their research and made other research opportunities available to them. And so we wanted to make something simple enough that people felt like they could build it and that they could build it, but robust enough to be used for real research. And I think that we've gotten to that point now that it's worked out a lot of the wiring issues and some of the coding idiosyncrasies at this point. And then on top of being able to put that together, making sure that it can actually detect plant changes and plant variability. So thus far it works. It's a little bit limited at this point in size for being able to use different cultivars or crops at different stages of growth. But part of the beauty of this is the adaptability. You can build it into or wherever you want to. That was part of the reason that we did it the way that we did. So the responses that we picked up were a little bit limited in regards to the cultivars and the cultivar responses being dependent on the stimuli that we imposed. But this opens up a lot of options for further research where we can either rerun these trials and we can ramp up some of the treatments to more extremes if we get the same results or different. There's the ability to add more indices. So I went back and ran all of my images through another pile of code that I wrote to try to pull more indices out, because initially I wasn't looking at the CFI because I was focusing so much on the NDVI, and it was per Dr. Seymour's suggestion that went back and started taking apart the CFI and the other wavelength indices to sort out whether or not those showed up. And the CFI is a lot more effective than the NDVI in the pH trial. And there are other researchers who are going to have more insights and interesting ideas and indices and wavelengths and things they want to look at that we may not have considered. And it's nearly trivial to add that to the system, which is part of the reason we built it. Another thing, I keep going back to the multiple cultivars, because from one trial, the Super Cascade Red was a giant mess in the first one. It was great in the second one, and vice versa for all the other plants. And so that's still bugging me just a little bit. But, and then on with those new indices, the other analysis options, going through and running for different wavelengths and things like that. So for my acknowledgements, I'd like to acknowledge Dr. Mark Van Ursel, convinced me to drag myself out here to the other side of the United States for this. And for Dr. Ferrarezi for adopting us when Mark passed, and for getting us over the finish line, and then to Dr. Mark Heidecker and Dr. Lynn Seymour for being on my advisory committee, and Dr. Heidecker for helping figure out all the technical problems, and Dr. Seymour for helping me figure out what my data is trying to tell me. And then also to all of my lab mates past and present who've either graduated or are still here. And then to my family for helping keep me sane. And this was funded by the Fred C. Glucker Foundation, pronunciation unknown, and American Floral Endowment and the Horticultural Research Institute. All right, as far as questions are concerned, let's start with the people on Zoom, but I hope the audio works. Anybody on Zoom? Oh, wrong button. Anybody on Zoom have any questions?
Hi, Kahlin, this is Savitri. Nice presentation. I just had one question in your first study about is there anything with your R-square values? I noticed that, would you say a certain R-square value, you would trust that to give a better response?
So if I increase the cost spent on the system, would my results improve?
No, I was asking you about your R-square value in your first experiment. If you look at the graphs, I felt like the R-square, yeah, with the NDVI, I thought it was decent, but the previous one, like just maybe a couple of slides before this. Yeah, this one, I'm wondering if there is a certain R-square value that, like the Super Cascade Red with 0.225 or the Wave Purple with a 0.488, would that actually, is that meaningful, that relationship, or not? Just curious.
Based on the p-values, I would say that those are meaningful. Though those R-squareds are pretty poor, you are not wrong about that. Though they're better than some of the ones I got off of the pH trial.
Okay, thanks.
You're very welcome. Does anybody else on Zoom have any questions? All right. Going once, going twice. Okay, anybody in the room got any questions?
In this figure, what is the criteria of getting the quadratic model? Why you didn't get the linear model? Especially for the carpet roof, it seems like linear, but you get the quadratic model.
There was a point at which I decided I was going to be consistent in all of what I was fitting, because for so much of this data, the quadratic is a much better fit. And so I elected to try to be consistent across all of my data points and just fitting a quadratic rather than switching between the two varieties. I don't know if that was a good choice or not, but it made it easier when I was trying to do all the analysis.
Normally, I feel like we should choose the method based on the performance, But I feel like your carpet roof and linear model better than quadratic.
Yeah, it's close. It's kind of a coin flip, yes.
So it was a great presentation. I really like your presentation.
Thank you.
But for about the NDVI thing, so you mentioned about you took pictures of many different kind of colors. And then how did you calculate the NDVI? I think that was missing on this slide. So
All right.
I'm very curious how you calculated it.
Yeah, so I have that slide, but I pulled it out because I was a little light on time here. Oh, come on. So if you guys are willing to bear with me for a moment. So this is how you get NDVI out. So NDVI is you take the intensity of the reflection at near infrared minus the reflection at red, and then over the sum of the reflectance at near infrared and red. So in this particular system, because we have each individual pixel and its location data, we took the red image and the infrared image, and we used the mask image and removed the background, and then we ran that equation on each individual pixel for the plant area, so then we could have a full spatial image of what the NDVI is for the entire plant. So we pixel by pixel, which is what allows us to have the quantities at the different intensities, which gives us an average for the whole plant.
So is that R referred to the reflection of the light?
Yeah, because for the image, all we're really looking at for the image is the light reflectance of a given pixel at a given wavelength.
So with that pixel actually represent the reflection of that light?
Yeah. Yes.
Okay. Thank you.
Yeah.
I have time for one more question.
Okay, sorry, go ahead.
Yeah, is it possible to measure chlorophyll A and B in imaging or total chlorophyll?
That is a good question. I don't know. I have to add that to the further research slide, I guess. Because there's a fun image that I don't have handy where we, at one point, a little bit before my time, doused a plant in something that actively killed photosystem 2, I believe. And in the chlorophyll fluorescence images, you could watch the structure of the plant change as photosystem 2 died. It's pretty crazy. So like you can see kind of what the chlorophyll's doing, but I don't know if you can do that precisely. Have to do a little more digging.
Thank you.
All right. Well, better get out of here so Peyton